Hello, IB students. Mr. Tima here. I took my face off this time because I think you're sick of looking at it. Just joking. Just put it on. This way you can see the full screen. There's some things that you might miss if my face was on there. But talking about complex vectors today, talking about complex vectors. Okay. Now, as we start going through, you'll notice that this part of our thing, these are kind of like what are our IB assessment standards, where those blue dots are. So basically, if you watch these notes or after we go through these notes, you should be able to go back and check off that you know what those blue dots are. And hopefully you can do that. So, what's a vector? Not this, but because in the movie, if you'd ever watched this, this is from oh goodness gracious, the Minions, the first Minions movie, and he says, "My name's Vector." Oh yeah, with magnitude and direction, and people laughed, of course, but that's really what the definition of a vector is magnitude and direction. Now, magnitude's a fancy word for the amount. Okay, it's the fancy word for amount, and direction's what it sounds like, positive or negative. All right. The first thing we need to know is the difference between a vector and a scalar, okay? So far, we've dealt with three different quantities, okay? Length times mass, density, all these. All of these quantities have size, but displacement also has directions, okay? Quantities that have size and directions are vectors. Those with only size are scalars, okay? So, for example, scalar is a quantity with magnitude only, or a quantity with amount only. A vector is a quality or a quantity with magnitude and direction. So, for example, for scalar, a scalar is like a weight. Okay, when you get on a scale, it tells you how much weight you are, but it's not really a direction. Okay, while like a force, a push on something might be 5 newtons to the right, which is very different from 5 newtons to the left. Okay, so for example, a scalar on this might be from A to B. Okay, or from A to B to C. What is your total distance? That would be a scalar. But your displacement, A to B maybe is 10 meters, and it's to the left, that becomes a vector quantity. This is all stuff you should have learned in physical science, so hopefully it's coming back to you. Again, usually we say up or north, down and south, right, left, and those have positive and negative quantities assumed with them in science, which you probably remember and already know. So the easiest way to do vectors is to add them. Okay, so for example, we can just add them. So, these don't have numbers with them, but basically anything to the right would be positive and anything to the left would be negative. And you can see down here at the bottom that the orange and the blue, since they're moving in the same direction, are added together and the red's kind of subtracted away. So our net would be that black line there, our net or our new total, if you will. The sum of all is what that becomes. If you're in calculus, we'd say that's our sigma force. All right, but the idea is that they're adding together. So here's a pretty easy one. If a train moves 100 meters forward along a straight track and then back 50 meters, what is the final displacement? Well, hopefully you got this answer right here, which is 50 meters forward. Okay, let's pretend it was flipped for a second. If it was 100 meters backwards and 50 meters forward, then we'd say it's 50 meters backwards. Okay, things like that. All right. Now, again, as we go with vectors, vectors are not always going to be straight lines. This is where your trigonometry comes in, your geometry with SOHCAHTOA and stuff. So again, we have to remember that when we try to find that, this is a great example of like a displacement problem. You walked 4 kilometers to the west and then 5 kilometers north. What is your magnitude and direction? Well, you would not say you walked 9 kilometers. That's your distance. Your displacement is that red line. Okay, your displacement is that red line. So how do we do that? Well, there's all this trigonometry formulas, okay, and you should know these. SOHCAHTOA, perhaps you've heard these before, where SO is sine equals opposite over hypotenuse, and so forth and so on. So if you haven't been using your trig lately, we're going to be using our trig. Okay, so for example, let's give it a practice here. It says find the side x of the triangle. Okay, well, x is on And remember, we're always talking in relationship to the angle. It's on the opposite side of the angle. This side would be the adjacent, or we say adjacent. Like when they say, hey, that car is adjacent to the building, means it's next to the building. Okay, so the X is opposite. So opposite, you're either at SO or TOA. Well, we have hypotenuse. So opposite and hypotenuse, that's SO or sine. So again, hopefully you were able to do that math. And again, if we get in class and you're having trouble figuring out how to do this math, I'll be happy to show you on your calculator and things like that. Remember Pythagorean's theorem. That's hypotenuse squared equals adjacent and opposite squared, or a squared plus b squared equals c squared. Okay, and here's just a quick example of how to do that. That's pretty basic. That's algebra 2 type stuff right there. So again, if you're having trouble remembering how to do that math, just ask. Okay, so what happens when things aren't kind of at 90-degree angles? Well, first of all, let's talk about how we talk about these vectors, shall we? This blue line right here, we're just going to imagine that it's 70 degrees, okay? And we're going to say the magnitude of it, or the amount of force that it represents, is 20 newtons. Now, we say that this is 70 degrees north of east. You could also say that this thing is 20 newtons, 20 degrees east of north, if that makes sense. Okay, this vector also equals 20 newtons, but we're going to say that it is 10 degrees south of the west line, if you will. You technically could say that it is 80 degrees west of south, but we don't tend to do that. We tend to go to what we call the airline model, which means like airplanes and everything. We talk about horizons. Ever since Newton, we've talked about horizons here. We know what a horizon is. So that's the 0 to 180 line. So we tend to come off of the horizon, or off of the zero, or down below the zero. Astronomers have been doing that forever. We don't tend to go off the north and south because it's very hard to just look at the horizon and know where straight up and straight down is. Okay, so when we talk about these directions, we're going to tend to come off of the horizon. Some of you are far smarter than me, like I've always told you, and there's these things called the law of cosines and the law of sines. If you want to use that, you're more than welcome to do that. You are more than welcome to use the law of sines and law of cosines if you're good at that. And there's nothing wrong with that. And they work faster sometimes than some of the ways I'm going to show you. But my way, or the physics way of doing it, can be used for infinite amount of measurements. And I'll show you how to do that. So here's the problem we're going to talk about in class. I'm not going to really explain it on this video because you're going to get lost. Okay, so what I would like you to do is to make sure you flip through this on the PowerPoint that's on Schoology, and also I'll go slowly and give a couple seconds here for each slide, and you can always stop and try to figure it out on your own. But we will be going over this example in class together, so don't freak out. The premise behind it's very simple. What if we have more than two vectors, and what if one of those vectors is not sitting at a 90-degree angle? Well, we're going to make what's called a chart. Okay, we're going to make this chart, and I'll explain how to use that chart. But basically what happens is you're filling in stuff based upon that. So just taking a second here. Again, you can always stop the video and try to figure it out. Basically, when we get our information filled in the chart by using our SOHCAHTOA, we add a cross, and that's why it's important to know if we're in positive and negative. And why are we positive and negative? Depending on our quadrant. Okay, remember, y is positive, x is positive, y is positive, but x is negative here, and so forth and so on. After you get your new totals, you basically make a new triangle, and then it becomes just a simple right triangle problem. Notice at the bottom, we have our new resultant force, and notice that our angle is 5.2 degrees north of east. We did not come off of the northern direction. We came off of the eastern or horizon vector. Again, we'll talk about these in class. Don't freak out. I will go step by step through this. Here's another practice problem for you. And we'll talk about that one in class as well. There's your answer. And we will do this one in class. You will practice it, and you should be pretty dang good by the time we're done with those two examples. The old riverboat problem. Okay, the old riverboat problem. Okay, the motion of the boat with the current. Okay, motion of the boat without current. Oh, I lost it. It's not on here. If we have the motion of the boat with the current, we're going to pretend the current is moving this way up to the top. Okay, we're going to say the river is moving this way towards the words at the top. So the motion of the boat is going to get carried over here to the shoreline. Motion without current, the boat would just come straight across. Okay, so you can ask yourself how to solve these three classic problems. Okay, we're going to assume that the boat is traveling due east, which means across, at 100 meters, and the river is pushing the river at 10 meters per second. Or excuse me, the boat is traveling across 100 meters at 10 meters per second, and the current is pushing down on the boat at 5 meters per second. So, how do we calculate the velocity across the river? Okay, well, we know that if left alone, the boat would travel at 10 meters per second. And if left it alone, if we just let the boat go and didn't move it forward, the river would push it down at 5 meters per second. Well, how do we find that resultant velocity? It doesn't just have to be a force, it could be velocity. Well, we're just going to use Pythagorean theorem. We know two sides of the triangle. Let's find the third. Okay, and then also we can find the direction, the actual degree at which it will travel as well. Okay, so hopefully that makes sense. Well, it says, what is the time required to cross the river? Well, it doesn't matter, and this is something that we're going to have to build on as we go through the class. It doesn't matter that we're being pushed downward by the current. It's going to take the same amount of time to travel straight across as it would traveling across and getting pushed down to basically where B is. Okay, I know that's hard to believe because what happens is it's like I am docked over here and I want to get to over where A is. And what happens is it takes actually more time because you're fighting the current. You're getting pushed down and fighting the current back. We're not fighting it. We're just getting pushed to B and seeing how long it takes. Well, if we know that our, shall we say, our velocity in the x direction is 10 meters per second, which was given to you, and we know it's 100 meters, then we know it should only take us 10 seconds to get across that river. And then finally, what is her displacement from A to B? So now we're trying to find this, right? We're trying to find this distance on the shoreline. I want to know how far I'm away from A than I am at B. Well, again, if we know it takes us 10 seconds to get across the river, then we know that every second our boat should have got pushed 5 meters down the river, if you will. So 10 times 5 is a distance of 50 meters. Again, you can draw triangles for that, separate vectors, all that kind of stuff, and we'll talk about that when we're in class. Hopefully that made a little sense to you. I know it's kind of hard when I'm not sitting up there on the board. Okay? Now, last thing, you'll have these as homeworks as well as that worksheet this week because we are in that 25% week. And I'll explain more of that when we're in class, and it's pretty well explained on your daily agenda. But other than that, I know that was a little bit of long notes, but that's why we're doing it online. I hope it made sense to you. If you have questions, reach on out. Otherwise, Tima is out.